The reason it's not available is because energy functions as a square of airspeed. It's not linear. As you can see, this is an actual chart. It's unitless in this case because the unit's not important, but this is calculated for a roughly 20,000 pound H-60, and you can see as the airspeed increases, the amount of energy increases geometrically. You'll also see along the bottom here the amount of energy that you would get back by decelerating 10 knots from each of these airspeeds. And what you can see is that the amount of energy available just by decelerating 10 knots, just by using the cyclic to trade 10 knots of airspeed, is double at 70 knots what it is at 40 knots. So you can see 1.6 to 0.8 there. 70 knots contains double the energy of 40 knots, and then all you got to do is get up to really about 105 or so, and you have quadruple the energy of 40 knots. And you can see here, as you start to get down below 50 knots, the amount of energy that you can get back by decelerating becomes almost insignificant, especially when you consider the amount of energy that's lost to frictional forces and mechanical forces, things like that. Each of these is just for decelerating 10 knots. So if you decelerated from 100 down to 70, you'd have 2.3, 4.3, 6.1 units of energy essentially recapitalized from that airspeed. Whereas if you were doing that from 50 down to 20, you're looking at 1.9, 2.5, a significant difference. And as an instructor, you want to think about what role that plays in terms of your defensive posturing when you're at low altitudes, slow airspeeds, or you could potentially droop the rotor system. The other portion of energy management pertains to the ability to add and subtract energy from the aircraft, specifically looking at power available versus power required regions and how that affects your defensive posturing and your risk acceptance as an instructor. Now, these are very generalized power available, power required charts. They're not specific to the H-60 or the Sierra. This is just your sources of drag totaled for your total drag and power available. This is kind of for a helicopter, and you could imagine this is being out of ground effect. So you've got your hoagie power here on the left, all the way up through your VNE, where the power available line intersects your power required. Now in this case, power available exceeds power required pretty well all the way through the spectrum, all the way up to whatever your VNE is going to be. Then you have a power margin and a power addition region all the way through. This is a great place to operate. If possible, you always want to be here. Reality is you might not always be operating in a situation where this much power is available. And so it's helpful to have a good understanding of how the aircraft behaves and where you introduce risk along the power available curve. So you can imagine, your bucket airspeed right here at the bottom, your lowest power required along the airspeed, and everything to the right of that is going to be your airspeed and energy stability region. So anywhere on this side faster than your bucket airspeed, if you're flying this speed right here, we'll say you're all the way up at VNE, you've got all the power in, and you're flying there. If you kept that power fixed and something came along, gust of wind, bumped the cyclic, something happened that caused you just to speed up a little bit from that point, you now are traveling faster than you can sustain with the power you have available, and naturally the airspeed will kind of come back from whatever you've sped up to that point and stay there. It will be stable. And the same thing happens the other direction. Something causes you to slow down momentarily. You still have that fixed power applied, and you will now have this kind of delta of power. That power set in there is more than the power you have, and as long as you keep the aircraft level, it will tend to speed you back up towards that fixed point. On the other hand, below that bucket airspeed, you're now in that speed or energy instability region, and you'll find anywhere on this side, really the opposite happens. So if you're at a given point along the curve there and something comes along that speeds you up, you will now have more of a delta there between the power required and the power available that will tend to cause you to speed up more. And that's fine. It's the other direction that you have to worry about. If you slow down, you'll now have less power available on that side, and that can cause you to slow down, especially if you've got a fixed collective setting that isn't necessarily here at our max power available. But where you can really get into trouble is if that max power available does start to come down. So if you're looking at a situation here, right, basically we're in an environmental condition where we only have essentially the exact power available required to hoagie, no margin above it. And this presents us with a situation that's pretty tight, right? This is definitely some place where you'd want to do a running takeoff and landing, or at least a max gross profile. But it also, as you can see, where you start to get into these areas where the amount of energy you're able to add to the aircraft becomes very small, and you can find yourself in this situation, and this is where you can really get into some risky business, is you find yourself in a situation at a higher density altitude, higher gross weight, where this is your max power available. This is full collective, and this is where it intersects the line. You're not hoagie capable at all. This is your minimum sustainable airspeed, and your VNE has now obviously come way down as airspeeds go. But this is where the speed instability side of the curve can really bite you, because as you start to slow down and reach this slowest sustainable airspeed point right here, if something causes you to slow down further, you are now slower than the slowest speed you can maintain, without any ability to add additional power to gain airspeed. So back to that original equation about our three sources of energy, the only way that you have to get back on the right side of that intercept point is to either give up rotational energy, to give up NR, or to give up altitude. And certainly if you're coming into a hover, you're making approach to a ship deck, you're working a vert rep load, that might not be available. Certainly altitude might not be available, and you might be forced to just sacrifice rotational energy turns on the aircraft. But as we talked about before, you've only got so many of those before you encounter that rotor stall condition, and then there's really no recovering from that once you hit it. So this is where you want to be, again, forming that defensive posture as an instructor. On the right side of the curve, more relaxed, not really guarding the controls very closely, maybe allowing the student to make some more mistakes, to try some things out, to see the consequences of ideas that they have. Start getting into that left side of the airspeed curve, that power required curve. Now your spidey senses need to come up. You need to start realizing your margins are smaller. The amount of power that you have to correct a student's mistake is smaller. And if you're in this type of power situation, you could get yourself into an unrecoverable state in which even if you took controls from the student, there's really nothing left that you can do. So as an instructor, you want to have a good understanding. Am I in this type of energy realm? Am I in this type of energy realm? Am I in this type of energy realm? And how do I leverage my posture in order to let my student learn, let them practice the maneuvers, but also provide that margin of safety by ensuring that if we're working down in these lower margin areas, I'm executing a higher level of oversight or of control for what the student is doing.